Let's look at the rapid delivery services as an example of the shortest path problem. The company operates a delivery service, and most of its business involves delivery of documents and parcels between offices during business hours. Now, when a customer calls with a delivery request, RDC quotes a guaranteed delivery time. The network below shows the routes that are available. So we have a route available between node 1 and 2, node 1 and 3, but we don't have a route between nodes 1 and 4 or 1 and 5 and 1 and 6. So the network is showing us what is available and possible for us to include in our path that we would need ultimately. The numbers on these arcs show us the time that it takes to go from any node to any other node. So for example, from node 1, it takes 35 minutes to go to node 2, and so on. From node 1 to node 3, it takes 30 minutes. So what do we want to decide? We want to know what is the minimum time that would be required to make a delivery between any two locations. So let's say from location 1 to location 6 as an example. So the first thing we'll do is we do realize that these are streets, and therefore let's assume, because we are not given any more information, let's assume that you can traverse the streets either way. So you could go, for example, from node 2 to 4, or you could go from node 4 to node 2 as well. So we will replace then all of these links with what we call directed arcs, arcs which tell you, or they are shown with the arrows, which tell you how are we proceeding. Are we proceeding from, for example, node 4 to node 3, or from node 3 to node 4? So you can see that that arc between, or the link between node 2 and 3 has been replaced by two directed arcs. We did not replace the link between node 1 and 2 by two arcs simply because we are not going to come back to node 1 in our example, because we are wanting to go from node 1 to node 6. So both the arcs from 1 to 2 and 1 to 3 have been replaced by a directed arc which goes out of node 1, but doesn't come in. And similarly for node 6, because that is our destination, we are not going to come out of node 6. We are only going to go into node 6. And therefore, those three arcs, which is from 2 to 6, 4 to 6, and 5 to 6, have also been replaced by a single directed arc. Now, all the other arcs on the network have been replaced by two directed arcs. So between 2 and 3, between 2 and 4, between 4 and 5, and between 3 and 5, the links have been replaced by two directed arcs because we can go either way. Now, this is the network that we will look at. Let's think about what the supply and demand will be in this case. So it's like saying that I want to send 1 unit from node 1, the supply node or the origin node, to node 6. So therefore, the supply at node 1 is 1 and the demand at node 6 is 1. So the node 1 is our origin node, node 6 is our destination node, and we are saying that they have a supply and a demand of 1 each. So you can imagine then we will see how to push this supply to from the origin node to the destination node at a minimum cost being time then over here. So what are we wanting to decide? We're wanting to know which arcs should we include in the route that we want to follow. So let's define xij to be the arc between node I and node j, and let xi take a value of 1 if arc I to j is taken on the route, and let it take a value of 0 otherwise. So again, it's a binary variable, or we just want binary values for that, which is 1 or 0. Let's think about the constraints. What would the constraints look like? From the origin node, which is node 1, we must leave. So if we must leave, then we must take one of the arcs coming out of node 1. So therefore, the sum of all the arcs xi to k, where k would be any node that is connected to node 1, should be equal to 1. For our particular example, the origin node is connected to node 2 and to node 3. So therefore, x12 plus x13 will be equal to 1. So that's our constraint number 1 for the origin node. Generically, that's how the constraint will look for an origin node in all other shortest path problems as well.